Pleasure to announce Sebastian Wieczorek from Cork, who is going to talk about zombie files.
Thank you very much. My voice is fading away, so apologies for this. I just found out that the microphone is not working for the room, just for the recording. Okay. So first of all, I'd like to thank the organizers for inviting me here. It's a pleasure to be here. It's a fantastic place, and for supporting my travels here. I will be talking about rate-induced tipping in a very specific example, the zombie fire model, a very simple zombie fire model. So what I will do in this talk, I will introduce rate-induced tipping, introduce different types of rate-induced tipping, and this example will turn out to be just one of the two main types. So be a mixture of some general ideas and some general techniques together with one particular example just to illustrate all those ideas and techniques. Now, this is work done in collaboration with my former PhD student Owen O'Sullivan and colleague Kieran Malcron from Cork. And the talk is organized in those 5 points. I start with short, brief motivation. Then I'm going to introduce the model and the concept of a moving stable state. And then I'm going to pose the research question for the talk, which is what sets off zombie fires? In the motivation section, I will explain what they are, if you haven't heard of them. Now, the remaining part of the talk will be more about mathematical analysis, so will be tougher going. And I will try or attempt to explain some of the main ideas that we use in the definition of rate-induced tipping and analysis of rate-induced tipping. We'll introduce some techniques there. And finally, we'll conclude. This analysis part will be part of some general ideas, and some of these ideas applied to global warming input into the model and a heat wave input into the model. So one, a very slow climate change, and the other is an example of an extreme weather event. So off we go. The main motivation is a combination of two environmental properties worldwide. And the first one is the content of organic carbon in peat soils. Peat soils is a bit like turf. These are very, very old soils going thousands or tens of thousands of years ago that sort of decompose in organic matter, and you find them below the surface, about 1 meter below the surface. And they are very, very interesting. They're actually quite complicated chemically and biologically, and also in terms of mechanics of those soils. So they are not fully understood. What's important for this talk is that they are very bioactive. There's a lot of microbes who live in those soils, okay? And these microbes are very sensitive to temperature or temperature changes, okay? So let's see where we have a lot of peat soils. These are the black dots. So you see Siberia, Northern Europe, Canada, a lot of it. Not so much in the southern hemisphere, but you see around the equator, because when you have a rainforest, you find a lot of them too, okay? So the other factor, which I want to consider, is the climate change, okay? So this color here, scale, is the rate of the warming in our world. It's quite recent. And what you find is that the world is warming everywhere, but particularly in the Arctic. And this is known as the Arctic amplification. So somehow in the north, the rate of climate change is roughly twice that in the remaining parts. So now you have this potentially dangerous combination of a lot of carbon. This is more than the current content of the carbon in the atmosphere altogether, stored in those peat soils, which are bioactive and temperature sensitive. And they happen to be in the part of the world that's warming the fastest, okay? So that's a bit of a dangerous combination. Now, by the way, this place Chersky in Siberia, there was just what do we do? Oh yeah, okay, so just has a delay, like in the previous talk. We're gonna take climate data from this place as a sort of proxy for our model, and I'm going to come back to that later in the talk. So the question that I want to ask is this combination responsible for what the media nicknamed zombie fires? Okay. So what are these? These are the fires that appear way ahead of the regular fire season, typically in the Arctics. And it started around 2010 in Siberia. That was massive fires. They still go on. And more recently, they sort of spread to Canada. So the last few years, Canada is sort of burning. Now, they start early, so they are very puzzling. Sometimes people just remove snow in the spring, and there is smoke coming from underneath the snow. So that can't be, you know, they scratch in their heads what's going on there. Now, they actually appear to be put out in the winter, but then they come back to life again like a bad dream the following spring, and it goes on and on. Okay? They're very difficult to put out because they're about 1 meter below the surface. Okay? And it's very difficult to actually deal with them. So you see there's some news from New York Times, blazes that refuse to die, zombie fires, that's the name. They're also called holdover fires in Canada. The Guardian goes up like tinder, unprecedented blazes in Alaska. So record high carbon emission in the Arctic. Now, there's a lot of talk about these fires and how they appear suddenly and for no apparent reason, and also where they are. But to our surprise, there's very little people asking questions. Okay, what's causing them, and what's the mechanism for these fires to come about? Also, they have always been around, but like in the 1950s, 1940s, they were very sporadic, very sporadic. And one characteristic about those fires is they become very, very frequent recently over the last 20, 30 years. So this correlation with sort of climate warming a lot, very, very hot summers, and this phenomenon. So we think that may have something to do with one another. And also peat soils, like a bit like compost, and compost is known for self-combusting, especially during very hot summer days. So we're gonna ask this question about what sets off zombie fires. And to do that, we're going to start with a very simple model. So now I'm going to the second part, the model. So we're going to look at the time evolution of the soil temperature and soil carbon, so T and C. And this is subject to a time-varying external input, which is imposed. And that's the atmospheric temperature. Very, very simple model. Okay, so what you have the equation for the temperature, the differential equation for the soil temperature. So the soil temperature balances towards the thermal equilibrium with the atmospheric temperature according to some cooling law. And that factor in front of that bracket, together with this epsilon on the left, which I'll explain in a moment, specify the rate of equilibration. Okay? But that's not all. Because of the microbes in the soil, when they become active, they can actually heat up the soil. As they decompose the organic matter, they generate a lot of heat. So if you ever go fishing and in the morning you go to compost heaps and you try to get the bugs, you sometimes see the steaming. This is the bioactivity. It actually creates a lot of heat. So the temperature can increase because of this activity. Now what happens with the carbon content? The carbon has been accumulated at a very, very slow rate, pi. This is plant litter decomposing over decades or hundreds of years. Okay? And the same microbial decomposition or bioactivity that heats the soil releases the carbon from the soil into the atmosphere. So you have a plus sign here, negative sign there. Okay? Very simple model. There's only one nonlinear term here. Everything else is linear. Okay? So it's actually very deceptive, because in a moment you will see that it's not so trivial. So there is two variables. T temperature is very fast. This is indicated by this epsilon, which is very small. And C is very slow. So two different time scales going on. And there is two input parameters. So they parameterize the atmospheric temperature. One is the magnitude or the amplitude of the change. So the difference between the initial temperature and some temperature later on. And the other is the rate parameter, which when you fix delta, it quantifies how fast effectively you are warming up or going from one to the other. Okay? Oh, thank you so much. So these are two important parameters for this talk. Okay? R and delta, they are inside TA. And there are three time scales. C is slow, T is fast, and TA, which is this non-autonomous input, it can be in between. Depends how fast it changes. Can be slow, can be fast. Okay, so that it depends what we are looking at. So intuitively, if you're a scientist, you look at this problem and you say, all right, okay, what's going on here? So what happens is you can think of a thermal equilibrium there, where T is in thermal equilibrium with the atmosphere. So not exactly at the atmospheric temperature, but nearby, because there is this extra term there, okay? So this equilibrium, thermal equilibrium, is moving over time now. So you have a system chasing a moving equilibrium, okay? And my talk will be about equilibria. I can generalize it to cycles and whatnot, but I'm going to stick with equilibria to get the main idea. And Hassan will tell you about the real stuff tomorrow if you find it interesting, okay? So this is what's happening. And there could be two different outcomes of this. The system either is able to follow those changes and chase the moving equilibrium, or may fail to do that. Because of this microbial activity, there's a chance of thermal runaway. So thermal runaway is like a vicious cycle. The microbes create heat. The warmer it is, the more they decompose, the happier they are. They create more heat, and so on and so on. Okay? And this is given by this function Rs of T here. So initially, it follows the Q10 law of the rate of chemical reactions. It's something very well known. Okay? And the activity increases with the temperature exponentially. But at some point, microbes die from heat because it's too hot for them. Okay? So this optimal temperature, and then it drops very sharply to zero because it's just too hot for the microbes to be there. Okay? And that's all the processes that I have in my talk. So I have these two competing processes balancing towards the equilibrium, thermal equilibrium, and potential thermal runaway. Okay? That thermal runaway will be truncated if it happens because they can't exist past this temperature. I must be taking way too long on each slide because I didn't see anyone else having this thing happening. Okay? I don't know what's going on. So now, when we analyze this system, we look at the frozen system. So you learn a lot from the corresponding autonomous system. Let's fix this atmospheric temperature, see what's going on for different but fixed in time values of TA. Okay? And then you find there's one equilibrium. I'm going to call it the base state or the cold state later on, okay, in the talk. And this equilibrium, its position depends on the atmospheric temperature TA. Now, this is hyperbolic and globally attractive for each of the TA within the range that I consider. Now, if you're not familiar with dynamical systems, you may not realize that this is the most boring of all possible nonlinear systems, okay? So if this guy comes in front of you, he's going to talk, they gave him an hour, he's going to talk about the most boring nonlinear system ever, okay? So that's really what it is, okay? So could a system be any more boring? No, not really, okay? But I said B, but I wrote appear, and everything is this word appear. It actually is very, very sort of deceptive. It's a very complicated when you want to analyze it. I'm going to explain why, okay? So what happens is there are metastable states, which is very fitting, for these workshops, and you can go to those metastable states. But they are, quantitative, they're not qualitative, they're finite time, and classical bifurcation theory or stability theory does not have the tools or ideas to actually pin them down and analyze them. So that's going to be the big part of my talk. So this is not all. I'm going to have this important concept, which is the moving base state. So because my TA changes over time, I can imagine that this changes over time. So the position of this equilibrium changes over time like that. Okay? That's not a solution to the non-autonomous problem. It's like a quasi-static approximation. So this is where the equilibrium would have been at every instant in time if the change was infinitely slow. Okay, so I'm going to use it as a reference frame, and I'm going to describe all the solution relative to this point of reference. So I have this moving quasi-static state, and the non-autonomous system is not quite there because the rate of change is finite. And the question is, how much do I lag behind my moving equilibrium? And if I lag behind too much, can things go wrong? If they can go wrong, there should be some quasi-threshold or threshold that separates two different types of behavior. What is it? So that's the idea. So let's sort of hit the road with some simulations. So first comes a RCP 2.6 scenario of global warming, which is quite a moderate scenario of global warming. So the change in the average temperature over 100 or 200 years by 2 degrees Celsius average. And you see there is a change of 4 degrees Celsius because I'm now taking this place in Siberia. Okay? And because of the amplification, the rate is twice the average. So what happens, here I have the moving equilibrium, okay, because the TA is changing here. This is the position of the temperature for the moving equilibrium. You don't see any change because it changes just a little bit on that scale. But what happens is the non-autonomous system, which is the red curve, follows this drifting moving equilibrium, but then something goes wrong. It deviates too far and goes to a different state that lasts over a decade. So how about that for a metastable? Would that be qualified as a metastable? Yeah, I think that's it. I'm safe here. So it stays hot for over a decade. And what happens during this time, and you don't see that on the plot, all the carbon is being burned, released from the soil into the atmosphere. And then when there's nothing to burn, very simple, the temperature drops down. And then very slowly approaches the moving equilibrium. Then there's a very slow rate of this carbon accumulation, which takes 200-300 years to accumulate back to what it was in the beginning before it can fire again. So it's a bit like a neuron, okay? So there are some sort of interesting results here. So first of all, there are other states than this unique equilibrium point, but they are metastable. You can be attracted to them, spend a long time in those states, but eventually you can guarantee that surely you will leave that state, eventually, after a long time. There's rate-induced tipping from the cold base state to this hot metastable state. If I change the rate of this warming, I decrease it, nothing happens. Okay. My red curve follows this moving equilibrium very closely. And if I cross a certain critical rate, well, there is no critical rate. But let's say if I go too fast, this phenomenon happens. And then, we're also the model is so simple. We put real data for climate and very precise experimental measurements for all the soil parameters in the soil. So it's a simple model, but it is conceptual model, but it is very close to people who measure in fairnesses in real life in terms of soil dynamics. So we're wondering, do we believe this? Let's compare it with the more complicated models. And there is a very good agreement with PDE models. So what I have here on the left, it's a slightly overlooked reference from 2008 by Korostianov and collaborators, when they considered a very complicated, so medium complexity PDE model of Siberian permafrost dynamics under climate change. They use different parameters for this microbial respiration. They are a bit too low, according to the experiments, so the warming is not very high. So what they see, they start from negative temperature of the soil, and they switch on the warming. Right? So you see the scale goes in hundreds of years here. And what they see, the soil responds by warming up to about 40 degrees Celsius and staying hot for over 50 years, over half a century, before it cools down. And in this process, it releases a lot of carbon into the atmosphere. So we just changed the parameters of our toy model to what they had, and I couldn't believe it really when Owen brought it. So it almost reproduces exactly what they see. Okay? So this PDE model focuses on the vertical pillar of soil, ours integrated model. But I have to say that what we put in the model actually captures all the key nonlinearities because this is almost identical. Yeah. Yes. Yeah. So this is we could do both. We could do both. And you will see in a moment how. Okay. And I don't have the numbers or the formulas, but we can talk about it. You see how this can be done. Okay. Now, so let's look at the summer heat wave. Previously, I had the global warming, no seasonal cycle, because the warming is a slow phenomenon, can average. But when you look at extreme events, which are short, you have to introduce seasonal variations in the temperature. So thus I have this oscillating winter, summer, and about that time I have a summer heat wave. That's my input. And this is what the system is doing. So the black here is the moving equilibrium. So the equilibrium moves back and forth a lot. System does not have enough inertia to closely follow those oscillations. So the system, the response is also oscillatory, but there's a phase shift, and the amplitude is much smaller. Okay? So you see the slow carbon, it's actually slowing things down. And then at this point, my equilibrium moves a bit higher. So it's a bit like in current stock, okay? But I didn't chop it off. So that means that the slope of this piece here it's much higher than the slope of that piece. So that's a kind of rate problem again. And after a summer heat wave, off I go to this hot metastable state, and I stay there. Now this state also oscillates slightly, but it's sort of negligible. And when the carbon is gone, I come back and I relax to my original cycle. So this is tipping from a periodic state. So generally, zombie fires are believed to be caused by surface fire that spread underground. Many people question this theory because it would require extremely high temperatures for the fire to spread through the roots so deep underground. Okay, so many people don't believe it. There's a lot of other theories that the campfire spreads, which some people say it's impossible. Okay, now we don't know what the reality is, but what we are proposing is that there is a sort of alternative explanation that this zombie fires could be a result of rate-induced tipping from a normal cold state to a subsurface hot metastable state in these active peat soils. Okay, and this is the result of changing atmospheric temperature, which is different from what used to be. But what's so particular about that today's climate, it's not so much the average temperature, but the variations and the extremes, like the heat waves, cold winters, hot summers, and so on. I mean, we experience it like the 4th heat wave in the UK right now. Sure.
When you talk about the rate, you're not talking about the rate of global warming, you talk about the rate of having a higher amplitude such that it comes up within 1 year, the rate of increase.
Yeah, so this realization, so I talk about global warming, that was example before, okay, this and this. And now I change my TA completely, no global warming, just a short time scale over 20 years.
Rate-induced is the rate within 1
year. Within 1 year, yeah. Exactly. Yeah, exactly. So this is the slope of the onset, how quick is this heat wave, okay? How fast does it go from winter to the summer? And of course, the way it goes, the hotter it is, then the amplitude changes the rate effectively, right? Yeah. So this is the situation here. So now, if you're a scientist, you can go home because you pretty much understand there's this sort of thermal runaway that's been truncated because the microbes die from the heat they generate. Okay, all done, sorted. But then you have these applied mathematicians put their hands on this problem, and they know they want to make things precise, they know how to complicate things. Okay, so let's do that now. Okay. And I'm going to ask some questions. I'd like to understand what's going on in terms of dynamics. So this is completely quantitative. There is no bifurcation going on because, look, in all these examples, whether you tip or not, you eventually, as time goes to infinity, you approach this cold state. So this is transient. It's like a forest burning up. Imagine you have a healthy forest at some time, and you're looking 500 years into the future. And you have two scenarios. In one scenario, the forest stays healthy, and in 500 years, you see a healthy forest. In the other, it burns completely, but then regrows within 100 years or so. So if you are 500 years into your horizon, you see a healthy forest in both histories, but one of them is drastically different from the other. So this is what we are looking at here. So this is this challenge. How do you define it? First of all, if you look at this non-autonomous system, and I will explain what it means, there's no compact invariant sets like equilibria, limit cycles, etc. Something that we are used to start with all stability analysis, okay? It's not there, so you're stuck at the start. Second, so if not, what do you do? So a natural thing to do, this is what people like Jacopo would do, they work with pullback attractors, and you can get some very good insights for one of the two types of rate-induced tipping, okay? Just for one. So this one is actually the one where you don't, okay? So we would need some other ideas. And let's identify instabilities of the solutions of interest. So these instabilities are not always bifurcations. So all this finite time business is actually, we are not equipped to analyze finite time instabilities, and that's what the talk basically will be about. So you have to make choices, and the big choice that we make for both the examples and the theory are these inputs, in general, in this case atmospheric temperature, which are bi-asymptotically constant. So it has to be smooth, so continuously differentiable, not a big thing to ask, okay? and then you can do whatever you want, can oscillate, even be chaotic, like you can take a piece of Rossler or Lorentz attractor, but the important thing is that as you approach positive and negative infinity in time, it actually converges to a constant. So all the theory works if you have this type of behavior. So there's a limitation, okay, because it has to decay to a constant, but there's also an advantage of working that because you have this notion of before and after. So the state sits, your system sits at some state. You don't have to be the equilibrium. Like current, you can use some initial condition nearby or whatnot. And then the disturbance comes on, does something, shakes the problem, and then goes away. So when it goes away, you're asking the question, where is my system? I take a building and an earthquake. Yeah? So before the earthquake, everything is still. Then the earthquake comes, the building rocks. Earthquake is gone, and the question you ask, is the building like this? Or is it like that? Okay, these are the questions are we going to be sort of asking here. So that also means, importantly for the analysis, that the system is autonomous in the limits, t going to plus negative infinity. Because when my t is positive or negative infinity, my input is just a constant. So I just have autonomous system with regular equilibrium points. Okay. Now, this sort of gives an idea. We're going to use the systems which are autonomous at infinity and have regular equilibrium points to solve the non-autonomous problem at finite time. Okay? And we do this through compactification. And I think I'm actually going to do it on the board to diversify life a little bit. I'm probably going to run out of time, but who cares? Let's just see. So we have that problem, okay? F of x. So x would be a vector c and t, but I'm going to do it a bit more general, less writing, okay? And my input I'm going to call capital lambda of RT. So this is a non-autonomous problem. There's this rate parameter. I want to have it, okay? Just so that you don't forget it's an important point. So now with those inputs, if lambda of R of t is asymptotically constant, you have two extra systems. So as t goes to positive infinity, you're going to have x dot is equal f of x. And now this becomes just a constant, which is, we're going to call it lambda plus, okay? Some for the future. So that has an equilibrium point. Great, okay. And as time goes to negative infinity, now this becomes another constant, we're going to call it lambda minus. So that also has an equilibrium point, okay, because there's just a unique equilibrium in the system. So you have two autonomous limit systems and a non-autonomous system in between. I would like to work with an autonomous system. So the typical thing to do is you introduce a new dependent variable, u equals RT. Okay, so then I'm going to say u equals RT, and I'm going to write the equation for, sorry, I'm just going to write it here. U equals RT, and I'm going to write another equation for u. U dot equals R, and I'm going to replace this with u. Now I have an autonomous system. Okay, the problem is I have three of them. So I would like to use the equilibrium points from this and that system to solve instabilities in this system. Okay, it's a bit messy. So this is a very elegant way of going around this problem. I'm gonna bring all these three systems into a single compactified system. Okay, and I'm gonna work with this compactified system. So how do I do that? I'm gonna define, instead of u, a different dependent variable, and I'm going to do hyperbolic tangent of some parameter nu, r over 2. So let's just do nu over 2 RT. So this is RT is u, right? So you can think of compactifying u. Okay, here u plays two times. Time plays two roles, the independent variable and the new dependent variable, okay? So this you do when your decay is exponential. So this transformation depends on your decay. If the decay is non-exponential, you have to do a different transformation. I will not go into the details into that. So you need to figure out the inverse as well. So RT, this is going to be equal 1 over nu natural log. I think this is 1 plus s over 1 minus s. So if s is minus 1, then log of 0 is minus infinity. Yeah, that's it. So this is it. And you differentiate this equation with respect to time. And what you get a different extended system. sorry, lambda. I'm going to leave it for a moment empty, and I'm going to have S dot is equal nu r over 2 1 minus S 1 plus S. So you can check that this works, okay, that this is possible to do. Now, my new variables are X and S, so I have U here, okay, so U is there, this is my U, and I can express U in terms of S, so I have to plug this in. So it's going to be my lambda of S, and how I get it, I just use this RT or U, this formula, plug into the argument of my lambda, and now what I have is an autonomous system that actually combines all three, because if, I'm just going to do for one of them, if S is equal to -1, S dot is 0, the same true for S being +1, so the -1 corresponds to negative time infinity. +1 corresponds to positive time infinity. S equals -1 or ±1 implies S dot equals 0, okay? So I have an invariant subspace. And this subspace carries the autonomous past limit system, because when S equals, let's say S equals -1, I have X dot lambda of S minus 1 is lambda of minus time infinity, which is lambda minus. When S equals +1, this is lambda of T positive infinity, which is lambda of lambda plus, okay? So you see what you have here, you have these invariant subspaces have the autonomous dynamics from infinities, and everything in between has the non-autonomous dynamics of the original system. So that's relatively easy to do, as you can see. Like I was able to do it in 5 or 8 minutes. And this is the main technique that we use for both the proofs of the general results. I will not be talking about them today, and also for the computations and for illustrations. So let's just go back to the slides now. There we go. So the second idea, first idea was let's use asymptotically constant input. Second, compactify, bring autonomous dynamics from infinity to negative and positive one of this extra variable, and use the autonomous dynamics from infinities to solve the problem. Okay, so this is exactly what I talk about. This is, I'm now going to leave the zombifier model, go to a different model to see what normally happens, okay? Because the zombifier model is not normal, right? So this is what happens for a predator-prey system, so herbivore plant system from this paper with Paul O'Keefe. The original model was proposed by Martin Scheffer and collaborators. We modified it a little bit. So this is P, this is H, so herbivores and plants. And at -1, you have this invariant subspace with autonomous dynamics. This is this equilibrium points, one stable equilibrium coexistence. This is extinction of herbivores, plants are happy, and there is some saddle which sort of defines the Bayesian boundary, the stable manifold of the saddle, okay? In the future, I also have this plane with invariant plane with autonomous dynamics and equilibrium points, okay? So now in the future, my base state, which is this one, also exists, but I also have the extinction state, and I have my saddle. Now, what happens when I increase time? So the idea is that I want to tip from this stable state in the past, okay? But you could take any initial condition. I'm just going to stick with that, okay? This is a very special case. So I look at just one-dimensional unstable manifold of this guy, because this guy is stable within that subspace. But S has to increase monotonically, because you think of it as time, compactified time. So it gains one unstable direction here, and this guy is stable, gains one stable direction there. So this is the only attractor. In addition to this, they're the only two attractors. These two attractors become saddles with one-dimensional unstable manifold. So this unstable manifold for small rates goes from E3 minus to E3 plus. I get tracking. I recover my coexistence state in the future. I'm safe. If the rate increases and is too fast, then look what happens. I start from the same point, but I go to extinction in the future. Okay, this red trajectory brings me to extinction in the future. And the question is, what happens between the two? Okay, so critical rate goes to that saddle. Okay, and that's a qualitatively different dynamics. That's a bifurcation. It's a global bifurcation. So we were able to reduce, using compactification, the qualitative sort of problem of rate-induced tipping to a quantitative problem to a qualitative problem of heteroclinic connection from one saddle to the other. So the saddle in the future we call the edge state. And again, can be much more complicated and so on. And people here in the audience use this terminology quite a bit, even before we sort of adopted from what people used in the past. So there is a bifurcation as I switch, my connection switches from here to saddle to saddle. And that defines a critical rate. Typically, it's codimension 1 in the rate, so just isolated points where these connections occur. And it gives you the critical rate, okay? So we can work with this manifold, and we have a critical rate. And it's defined by this heteroclinic connection from E minus to some edge state in the future, okay? Sorted. That sounds great. But there's a reason why I did the detour. Because if I go back to the compost, sorry, I keep on calling this compost bomb problem, because that was our first problem. To the zombifier problem, there was a bit of a bummer. Because these are the invariant subspaces. This is the future, this is the past. And there is no edge state. It's just an equilibrium. So compactification is very useful, but it doesn't solve the problem. Because where is the edge state, okay? Now, this B connection from E minus to E plus exists for all values of the rate, okay? Small or large, and the change is only quantitative. So I have this quantitative R-tipping. There is no loss of endpoint tracking. In the end, I'll always come back to the same state for all the rates, whereas in the example before, my final state depended on the rate because there were alternative states, and the critical point was the saddle. If you forget about that guy and look at the excitable system, it goes to one attractor for all the rates except of the critical where you go to the saddle and then you go back. So there's always a qualitative change. Here, no. So look, we need to do some more, and we're going to exploit these different time scales in the system. I said that some variables were slow, some were fast, and I can introduce an edge state. And it's a bit funny if you haven't seen this before. There are special points in the system that you can't see, okay? But if you sort of go into the singular limit of epsilon being 0, you can find these points in the singular limit, and then you can define the rates in terms of heteroclinic connections, which are quite exotic, from E minus to those very special points. Okay, now that gets quite technical from now on. Okay, it's a bit too much for after lunch, but so to start with, I'm looking at global warming to start to warm things up. Okay, so what I have what I call the slow manifold. So if I take a step back, you see that this sort of jumps to some high temperature object, stays there for a long time, and then jumps quickly back, okay, and settles down. So when you take the limit of epsilon going to 0, for the case where you have 2 slow variables and 1 fast variable, so what's happening now, my soil temperature is fast, and my carbon is slow, and my S is also slow, because I'm looking at a very slow global warming. S carries the time scale of the input, this extra dimension here. So you have 2 slow variables and 1 fast. I have a two-dimensional slow manifold with this S shape, so very, very commonly seen. So it's got one attractive part here, S1. There's a fold. There's a repelling part, S2. And there's another attractive part, S3. This S1 contains my moving cold state. Okay. So if I change at the low rate, I follow the moving cold state. This is the green one. You want to be away from that fold, because when you cross that fold, the fast dynamics will very quickly bring you to the hot metastable state. So when you go too fast, you slip off that fold, you go to the hot metastable state, and you follow the hot metastable state, and then when you go through the other fold, F2, you sort of jump back, and so on, okay? And there's very special solutions called canard solutions, which follow, for some surprising reasons, the unstable slow manifold for as long as it exists. This is a maximal canard. And it's not just one of them. There is canards that follow the unstable slow manifold for some time, jump to the left. They're called canards without head. And there are other canards that follow the unstable sheet and jump to the right for a little bit. And they're canards with head. So the transition from one to the other is not a single critical rate. It's a range of rate, which is very narrow, exponentially small. So it depends on epsilon, the small parameter. And it has all these intermediate solutions, okay? So let's now define things a little bit. That's still a bit hand-wavy, but it's good enough for the talk. We track if we never leave S1. So if I never leave S1, I'm tracking. We tip, our tip, if we visit S3, okay? And you recognize that there is actually a continuous family of solutions that do neither. So solutions that leave S1 but never go to S3. These are those canards without head. So you follow the unstable one, so you left S1 and then you go quickly to the left, okay? So there's a whole range of this. And you got the definition, okay? We had to work a bit hard to get this, and then let's try to do some simulations. So this is the magnitude of the global warming. This is the rate of that. So we use we use the tanh function, and you see that when the rates are very, very low, you always track. You're in the green region. When the rates are higher, you have to have a change which is big enough. So there is some kind of asymptote here. Okay, the temperature has to increase far enough. Once it's far enough, there will be rates, critical rates, that will bring you to sort of tipping. And this blue range, canards without head, it's actually very narrow, but note the logarithmic scale. Okay, that's why it appears a bit wider. This is where you have neither. You have this transition. So looking at that, there's some funny things, because this is just a clear-cut transition, but this R-tipping tongues start to appear for the larger values of delta. So there's some change going on there. It's actually difficult to tell. So what you can do, you can analyze this. You can analyze this, and the question is how to capture this quantitative change, okay? So there are no bifurcations, and what we're gonna do, we're gonna set epsilon to 0, obtain the reduced problem. So I need to derive some problem, slow dynamics on that slow manifold. That's a mathematical exercise that one can do, okay? I'm not gonna do it here. And identify special points like canard points, and you will see what happens there. So maybe before I show the complete picture, I'm gonna have the heteroclinic connections from E minus to a special point called canard point or a folded singularity that does not exist in the original system, okay? I can only reveal it in the singular limit when I do derivation of a special reduced problem on that slow manifold. So now you're looking at the first fold of the manifold, okay? So this is the manifold. This is the moving cold state, and you're worried about so this fold sort of in time goes down, you're sort of lagging, you can slip, okay? So what I turn it like that, and you're looking at the fold from the top. So these are the squares here that you see, okay? That's what we are looking at. So this is E minus past, E plus future. This is the moving fold, this is the moving cold state, and the red is the trajectory, okay? The unstable manifold of this guy. For small rates, I sort of stay away from the fold and I track. But the special points appear on the fold. This is folded saddle node singularity type 1. I say it's a bit of a tongue breaker. It's a saddle node bifurcation on the fold of canard points, which are not equilibrium points, or that they don't mean anything. They don't exist in the original system. But here I can make them look like real equilibrium points. So I create additional equilibrium points, okay? So here I'm safe. When I increase the rate, I open this channel that brings me to the part of the fold which is attractive. Now my initial state is not in this region, so I'm still safe, but that region is there. So if you're looking at the initial condition away, you may already be hitting the fold and tipping. So this is how you scale. It's not a trivial problem, but with this you can estimate how much time it takes by looking at these things, okay? Depending on where you start. Now there's a special rate where the basin boundary of this dangerous region hits my initial condition, and the unstable manifold actually becomes the maximal canard. And past that, I'm in the red region, so I'm bound to hit that fold and jump and have a sort of tipping. So that's what sets off zombie fire in the compost bomb example, okay? Now, turns out that there's two cases separated by a very special point. It's a lot of mathematics. I'm not going to go through it. Let me just tell you that this is the simple case. This is the complicated case, okay? So that's sort of has to do with, here I interact with so-called folded saddle singularity. This is folded saddle. But also much more complicated folded node singularities with very complicated canards, not fully understood, by the way, okay, by the experts. So that's, it looks very, and remember how deceptive that original problem was, okay? Just now we ended up with problems that, experts in slow, fast systems don't understand fully. I mean, isn't that amazing? And there is a special case, the degenerate case that separates these two. Now, if I go back and I plot these exotic heteroclinic connections, I can explain these simulations that I've seen before, okay? And where I get two cases, the simple cases here, I get this tipping tongues is the complicated case. So now I understand why I have these tongues and the situation changes, because I go from one mathematical case to a different mathematical case, okay? I'm gonna skip because I'm running out of time. And if I do the heat wave, things are a little bit easier, okay? And I'm gonna just say a few words and conclude. So for the heat waves, things are easier, and the reason they are easier, you see this is the result, but I'm gonna tell you going back to the board. I have T being fast, C being slow, and now because it's a heat wave, it's just few months, my input, which is the S, is also fast. So the different problem, two fast variables, one slow. So I don't worry about the slow manifold anymore because it's not important. I take a different limit of epsilon going to 0 for different time, rescaled time, and I get this layer for a fixed carbon. So carbon is so slow, when the important things happen, carbon doesn't change so much. That's so slow, okay? So you see that it's a good approximation of what happens in that layer. If I shoot from here, in the positive case, I track. In the negative case, I tip. Okay, here, so I'm almost in the layer. Everything that falls is just this slow, transient, metastable state, and then you come back. And in the intermediate case, I have this special canard where I hit the unstable manifold of the future limit system, and I have the situation. So it's a bit different from previously because important thing happened in that layer. If I reduce myself to that layer, what do I gain? I don't have folded singularities. Actually, I have new equilibrium points in the layer. So every time I have a metastable state, in this limit, this metastable state becomes an asymptotic state because I am freezing the slow variables, so to speak, okay? So I don't allow this to vary. So I have an equilibrium here, which is stable, that corresponds to the metastable state. Now it's frozen, metastable state. This equilibrium remains an equilibrium, and because of this unstable branch, I get a saddle point, a real saddle equilibrium in the layer problem, which is also easy to derive. So when I do the simulation, I get now a more interesting thing. For slow, I track, then I tip, then I track again. So it's kind of resonance phenomena. Intermediate rates for the up and down, give you this optimal situation when you tip, but then if it's too fast, the system has no inertia to respond, and you track again, okay? This complicated stuff is there. And if I look at the layer problem, I can see that, I'm safe here. I have a heteroclinic connection from this equilibrium to that saddle. That saddle, exists only in the layer problem. It does not exist in the original system. So again, a heteroclinic connection from something to something else. None of these things existed in the original systems. These guys come from compactification, and the other structure comes from the singular limits or the regular limits and so on. And this is a funny situation because this is what happens when I go fast. This is what happens when I go slow. When I go fast, I track. When I go slow, I tip. So Jacopo calls it rate-induced tracking. But in our definitions, it's tipping, and you can understand it because on that layer, I can separate the timescales again, and what you have, just one last insight, you have this situation on that layer. So this is stable, stable, unstable. So if I go very fast, I jump the gap and I save myself. If I go too slowly, I fall here and I track some other state, okay? And you see some faint curves here that give you that gap in this vertical orientation. And this exactly just fall into that gap, or you sort of make it and then you recover, okay? This is what I was talking about, this tipping points not being falling off the cliff. You can actually jump the gap, if you will. Now, bringing it all together, these are the exotic heteroclinic connections that explain the diagram that we had from numerical simulations. I'm going to skip this one. So just to conclude very quickly, I try to explain to you what the different types of rate-induced steeping are, okay? And I gave an example which is quite sort of intricate. It looks very, very simple, but it's not. And potentially very, very interesting and important, that is the complicated type of rate-induced steeping. We have a nice theory for the first type. We are working with Pete Ashwin on the theory for the second type, and we are getting there, but it's going to take a few more years, okay? So, which is okay in our business, okay? Analysis compactification geometric singular perturbation theory allows me to turn this quantitative system with no classical bifurcations whatsoever into a qualitative problem of possibly exotic heteroclinic connections, okay? If you start from an arbitrary initial condition, you have a connection from that condition to some saddle in the future, okay? Still have a connecting orbit, doesn't matter where you start, okay? I showed the results for equilibrium points. You can easily generalize this to more complicated compact invariant sets like limit cycles, tori, chaotic attractors, and so on. And some people work on that. I should say that excitability is a concept that comes from neuroscience. You know, you perturb a neuron. If the perturbation is small, it stays quiet. But if it's strong enough, it fires. And that's a super nonlinear response. Unfortunately, some climate systems and Earth systems are also excitable, except when they fire, okay, it's a bigger problem. And this is an example of an excitable system. This zombie fire simple model is an excitable problem. You have this excitable response. Now, what happens here, we actually, by studying these things with these techniques, you can uncover new types of excitability thresholds. Okay, so I didn't talk about that, but some of those canards were just new types of excitability thresholds. Now, my heat wave example for the analysis didn't have the annual cycle. So if you want to see the heat wave problem done right and see how this becomes rate-induced phase steeping, because you really depend whether the heat wave is in December or June, then you come to Hassan's talk. And I think with this advertisement, I'm gonna finish. Thank you for your attention.
Thank you, Sebastian. It's fantastic. Very interesting. Questions, please.
Yeah, thanks for the talk. Is it correct to say that R-tipping does not require multi-stability, but endpoint, so R-tipping with endpoint tracking does require multi-stability?
Yeah, so we have two main concepts. Endpoint tracking, meaning that in the limit of t going to infinity, we approach to some stable state, okay? And there are two types of rate-induced steeping. One is this qualitative, meaning that there is a rate at which you fail to endpoint track, okay? And that can, again, be irreversible. You go to a different attractor, or reversible. You have an excitable response, and you come back to your attractor. So in the excitable case, you endpoint track for all the rates except the critical ones, because at the critical ones, you're at the edge state. So this is one type of R-tipping. This is sort of qualitative, but there's also quantitative, where there is a change in the magnitude of some variables, but there's absolutely no change whatsoever in the endpoint tracking. You endpoint track for every value of the rate. So that's basically, these are the two types. And the first one has a unique threshold, which is defined by the edge state. It can be very complicated, but there is a clear-cut threshold. You often, when you have complicated dynamics, you can go tracking, tipping, tracking, tipping, tracking, tipping, because that threshold can be fractal-like even. So it can be very, very complex and accumulate on itself and whatnot. In the quantitative one, the one that I described, there is no threshold, but there is a quasi-threshold, which is like a range. Okay? So you think of maybe layers with thickness of those Canard solutions, and there's a range of critical rates. And again, you can have many ranges. I hope that answers that.
Okay, but so then in the future limit system, then you would have multiple states there if you can have different endpoints, right?
Yeah. So so the important thing is that you have loss of endpoint tracking means that you either go to a different attractor or you go to a saddle. Okay, either can be. So the saddle is special at the critical rates, other attractor is typical, away from critical rates.
More questions?
Very nice talk, especially like the last part is very new to me. One thing is, I think, especially in this case of the canards, actually, I think I'm pretty sure you would see a change of finite time Lyapunov exponents for the trajectory, which means practically also that like little uncertainties of perturbation would also produce very different scenarios. So what do you think? I mean, how, because this also, in some sense, you could consider it in some type of local application.
That's right. So I think when you do some simulations, right, and you want to be a scientist, I think it's a nice way of looking. Now, I'm not sure about this finite time Lyapunov exponents. So the results from Lyapunov are asymptotic results again. Then you have an exponent and you can ensure that it converges if you wait long enough. Now, I know people work with finite type Lyapunov exponent, and I think either finite type Lyapunov exponent or just checking divergence, you will see a huge change in divergence actually from negative to positive as you start crossing. So you can track divergence, which is divergence tells you how fast is the volume of the phase space expanding close to the point where you compute the divergence. So rates of contraction or expansion, okay, this is what you get. So there are measures to see that this is happening, okay? Now, to make it rigorous and to make some statements, we went with this approach, okay? Because then we can really prove things. But for all practical reasons, I think divergence, finite type Lyapunov exponents would be fantastic tools to actually apply and analyze and see what happens. I don't remember who emailed me about it. Some people checked it, and there is a change in the sign of the finite type Lyapunov exponent. Yeah, and so you know exactly. Yeah, exactly.
Since we are just at this figure, so I didn't get where this saddle point, where the blue trajectory, so to say, goes to really comes from, because you are projecting basically first of all everything to this layer. So you have the two fast variables, and everything happens there because the slow one is basically constant. But so the saddle point, so where does it appear? So to say, in this.
So this is what happened. This is the full system, right? Before I do the layer. So this is the full system. I just wait for the system to come back online. This is the full system, and I want to look at the layer. Okay. So the layer is that gray surface here, and in the past and in the future, I have these slow manifolds, which are my quasi-static states or metastable states. So you see that the layer intersects this metastable states at 3 points, 1, 2, and 3. The layer is chosen to be the level of the original equilibrium. So this intersection doesn't give me a new equilibrium because I already had an equilibrium there. But this intersection of the layer with the unstable slow manifold creates an unstable fixed point or an equilibrium. Because what the layer does, it basically freezes slow dynamics. So normally I should be drifting slowly here, but the layer, what it does, it actually fixes it. It gives me an unstable point. So it's the intersection of the layer and the slow manifold in the future. And this intersection of the layer and the slow manifold gives me a stable equilibrium point. See, it intersects with the stable quasi-static state. But this intersects with I don't want to call it, because this is metastable. I don't have it. This is like meta-unstable. You know, I don't know what the name would be. But because it's a saddle, you can get there. So meta-saddle state, metastable state becomes saddle equilibrium and stable equilibrium. This is where they come from. Does that answer?
Yeah.
Yeah. Okay.
So probably the last question.
I know exactly. Yeah, I think so. Jerome also wanted to ask. It's okay. Okay, so thanks a lot. So very interesting talk. So my question is, so you have very fine picture, so what happens and so on. So what happens if you add noise? Because noise destroys very often things. So sure. Will this picture survive?
Yeah, absolutely. So what happens is that where the noise will have huge effect. Normally what happens with noise is when you have a clear-cut critical rate, you sort of make a range of critical rates with noise. You smear it out. Here you already have a range. So the noise will destroy this canard trajectory. So the transition from tracking to tipping will be more blurred than normally. Okay, but the phenomena persist. The really interesting question about noise, when you really think about noise in the context of this application, right? So that's the general answer for the noise. If you look at this, we have a perfect summer-winter cycle, but it never looks like that. So to really do this, instead of imposing a heat wave on a perfect sine time series, you should take proper data series from the Met Office or Met Iran in Ireland where we live, okay? And they also will look like that with the hot summers, and subject the model to the actual input of the actual data. And that will be noisy because some summer will be hot, some will be cold, and there will be winter, have a warm episode. So this noise will be very interesting to see what that does from the point of view of these applications. But theoretically, the system is very sensitive to noise only in the transitions, and you have to ask things differently when you have noise, because it's a sort of stochastic problem. What is the probability of tipping by the certain time? Because if I add white noise, the probability of tipping, if I wait long enough, is 1. So the questions you ask, more like an ergodic theory type of question. What is the probability that I tip within a certain time window for this type of noise? And as you formulate questions slightly differently, and do maybe analysis which is a bit different.
But sorry, I can still ask questions.
Yeah, sure.
Isn't it here that you just trigger this? You just have to go over the ridge. So if you get one peak, you don't need statistics. You
No.
say if this input signal has something that kicks you over the ridge.
That's right. But it's not so easy because it's where you are at the moment. You're not at the equilibrium because things change. So you're not at the equilibrium, and actually you don't know relatively where you are with the ridge. It's not so simple, yeah. But it's a pretty much intuitively, yes.
Critical one that if you're above something for sure,
That's
you
true.
must jump.
That's true. I agree. Yeah.
Okay, I guess we have to finish. So, all other questions keep until the break. So let's start.